Thanks, Brian, for that nice introduction. So indeed, I will be talking about how social networks filter information. This role that social networks have has only been amplified by social media, and I wanted to tell you what the consequences of this are. Now, first I'll tell you about another experimental Facebook study. This time we want to know what is the social influence of your friends on your information sharing behavior, as opposed to your, say, voting behavior. And this study was conceived by Eitan Bakshi and was done in collaboration also with Itamar Rosen and Cameron Marlowe at Facebook. This is the basic setup. You have Bob and Alice. Bob is into networks, Alice is into networks. This brings them both to the Network Science Conference last year. And they get along well enough to become Facebook friends. Now, sometime this year, Alice posts about this year's conference. Bob sees it, and then he decides to post about it as well. What we would like to know is whether if Bob had not had a chance to see Alice's post, would he have shared nevertheless? And what Eitan wanted to know is, can we experimentally simply manipulate this, whether or not Bob will see Alice's post, and then can we measure the probability that Bob will share, given either that he sees it or he doesn't. And this will help us distinguish things such as actual social influence versus just correlations due to homophily. After all, the reason why they're friends is because they have this interest in networks, which then also correlates with their sharing behavior. So this is just what I just said. Just to reiterate, this might be your Facebook feed, and we are going to randomly block out some of the stories. In this case, it's a CNN news article about an iPhone app that automatically detects potholes and sends the info to the city of Boston. And then we're going to see, are you going to share it anyway? How could that happen? Well, maybe you just have an interest in potholes, and you're reading CNN, and you decide to share that article, regardless of what your friends are doing. Now, this experiment was run during a 7-week period in 2010, and the resulting data, even though so few of the subject URL pairs were filtered, it was still very large. So you had 250 million different subjects, 76 million different URLs, and over 1 billion distinct subject URL pairs. And we have two ways of measuring this effect of social influence. You have the average treatment effect, which is simply the probability that you share if you see the URL in your feed shared by your friend, minus the probability that you share if you don't see any of your friends' posts of that URL. We also can look at the risk ratio. For example, when you're looking at the risk of developing lung cancer, if you're a smoker, it's about 20%. If you're not a smoker, it's about 1%. The average treatment effect in this case would be 19%, but the risk ratio would be 20 times. You're 20 times more likely to develop lung cancer if you're a smoker than if you're not. And indeed, in this experiment, you are influenced socially by your friends. So if you see a URL shared by one of your friends, you're 7.3 times more likely to share it as well. OK, that's great. But James mentioned that you have your close friends and your not so close friends. In other words, your strong ties and your weak ties. And the idea here is that you have your close friends who are likely to be sharing things that are going to be of interest to you, but because of this homophily compound, maybe you would have shared them anyway. On the other hand, you have your weak ties. They may be sharing things that you're less interested in, but you're also less likely to have discovered them independently. That is, they're bringing you novel information. What we then do is much like what James described, which is we use proxies for tie strength. And here we're going to keep them separate, but again, they're just measures of interaction. How many comments did this person leave on your posts? How many messages did they send you? And how many photos were you both tagged together? And we find that regardless of which particular measure we use, Actually, should I try and, this looks pretty bad, right? Should I try a different resolution or something? Or is it, how's it look from? What's the native resolution of the projector? Does anyone know? Yeah, but James's slides looked good. Okay, just one sec. And displays. Okay, so 800 by 600, you're saying might not be the right one? Maybe this not stretched? That looks no, wait. This one? Is that it? Uncheck, okay. Okay, I'm not hearing, okay, we might just have to live with it. Yeah, good, okay. Sorry about that. Is that worse? Oh, makes me so sad. Okay, so what you find is that as the tie strength increases, for example, the number of comments that this person has given you in the 3 months prior to the start of this experiment, the greater the tie strength, the more likely you are to share that URL when you see it from that friend. So strong ties are more influential. However, you're also more likely to be sharing it independently. Again, they're sharing things that you might be interested in separately and discover on your own. And indeed, if we look at the relative risk ratio, it actually falls as a function of tie strength. And this captures exactly this effect that your strong ties, you trust more, you're going to follow what they're doing, but what they're doing may be what you're doing already. And now we want to aggregate this effect. And what we're going to do is we're going to count the number of weak ties that you have and count the number of strong ties. And we're going to give strong ties as much of a kind of running start as we can. So anyone who's interacted with you in any of these ways at all is going to be a strong tie, and everyone else is going to be a weak tie. And we're going to multiply these numbers by the average treatment effect. That is the influence that we measured, subtracting out your independent probability of sharing. And what we find, regardless of the particular metric that we use, is that weak ties account for more of your information sharing behavior that's due to social influence. So what does this mean? It means that actually information exposure on Facebook is relatively diverse, and this is thanks to your weak ties. Now, did I try and slip something by you? There's this slide with the risk ratio where I said, ooh, 7.3% or 7.3 times increase. But if you looked at the percentages, your probability of sharing a given URL that shows up in your feed is actually just 0.25%, which isn't really very much at all. So would you conclude that information is not spreading? Well, in fact, it is spreading, and Facebook is being an effective filter. Because imagine if, for example, you're interacting just with 20 friends on Facebook who are showing up in your feed. If the probability of resharing their URLs on average was something like 5%, you would get these great epidemic outbreaks of information on Facebook, because the replication ratio, meaning how many individuals does one individual infect on average, would go above 1. And so all we'd be doing all day on Facebook is forwarding each other's URLs. So in fact, things are under control. We managed to successfully filter a lot of information. However, there are some things that we don't filter as successfully. And these are memes. So are we playing with the information, or are we being played? The title slide had this graphic, and it is actually the very initial diffusion of the what my friends think I do all day meme, and this is the professor variant. Now this meme, if you follow it just over the next couple of days, looks like this. This is the first 100,000 people who shared just this variant, the professor variant. It eventually reached over 1 million different people. So clearly some information we're very susceptible to. Now, rather than studying image memes, my collaborators Tom Lento and Eitan Adar and I studied text memes, and the reasons for that will become apparent. The text memes are of the form, for example, this one I'll discuss in detail, no one should die because they don't have health insurance and blah, blah, blah. If you agree, copy and paste this to your status. So they propagate not by clicking reshare, but through a copy and paste mechanism. Prior to about April 2009, these memes were almost absent. And I thought, oh, there's some sort of bug in my code. It turns out that actually the Facebook status update was an inhospitable environment to memes. And the reason was that there was a 160 character limit. So once you've already used up the 15 characters for the copy and paste, there's not much room left for the payload of the actual meme. As soon as that character limit is lifted, what you have is a meme that comes about, it's a blood drive. Following the earthquake in Italy, it says, if you can, call this number, if you can donate blood, and there are 40,000 copies of this going around. Now, not all the memes are as beneficial. Around the same time, there's a meme in Danish saying Facebook will start charging, which wasn't true then, and it's not true today, even though this meme persists in quite large numbers for over a period of several years. Other fears that they play to these memes, for example, there was a single jar of baby food produced and sold only in France that was reported to have a piece of glass. It was recalled. However, once the meme got into Facebook, it was translated into English and started propagating. And at some point, it even became Gerber instead of Nestle, right? And just happily propagated further. Now, we're not defenseless, right? If you actually use a search engine to look up any of these memes, it'll tell you, what's up. This isn't exactly true. No, Facebook will not start charging. But the memes have other tricks up their sleeves. So if fear's not going to do it, guilt. So you would propagate this Amber Alert if it was your child. So here's a parody of the memes. It's got to be true. I read it on Facebook. Please read carefully. 98% of you won't repost, but I'm sure I know who will be a true friend, blah, 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 right? It turns out that this kind of challenge formulation, X% won't, but the Y% who are truly awesome will, gives a 50% boost in whether that variant of the meme will propagate, right? So you have the same meme, it's saying the same thing. One of the variants says, 97% won't, that one will have the better propagation. They also try and manipulate the timing. So they'll say things like, you must copy and paste this within 11 minutes of reading, or they'll say, keep me around for a while. So if they have a formulation such as for at least, they'll tend to have a 2 times boost in propagation just for having that phrase, the variant that does versus the one that doesn't. So what I'm saying already is that these memes adapt, right? They tweak themselves here and there so that we propagate them. So for example, with image memes, if the professor one you can't identify with, well, maybe the Mac user one you can, right? So maybe that is the one that you'll propagate. A lot of the variations actually use humor or parody. So this is a parody of the Facebook will start charging meme that says you must do all sorts of ridiculous things, and only then will Mark Zuckerberg come down your chimney and personally guarantee that Facebook will never start charging. And the parody became so popular, 100,000 copies, that in fact people then became quite irritated with it and said, don't know what's more annoying, the original, false meme or this parody of it. So let's get into how these memes actually spread. And here is a particular meme which I already mentioned. It's in support of Obama's healthcare plan, basically saying that no one should die because they can't afford healthcare. And this is what I was afraid of. This is how it got started. So a single person here posted it. It spread to their friends, who then copied it and copied it, etc. And from there, it grew, and it grew, and it grew, and it grew. And this is all in the span of a day or two. And after that, it kind of declined, but it stayed around for over 2 years. And it also did not get copied exactly. So over time, you get different variants. So here's the original, but maybe you don't care about politics. Maybe you don't care about the healthcare issue, but you really like beer. Well, there's one for that. So no one should be without a beer because they can't afford one, and no one should go broke because they bought too many beers. Not into beer, what you run on is coffee. Well, oh, sorry. There's a coffee variant. No one should fall asleep because they can't afford coffee, and no one should lag behind because all they can find is decaf. Neither beer nor coffee do it for you. Well, there are lots and lots of zombie fans out there, so no one should die because of zombie attacks. But if someone gets infected, the right thing to do is shoot them. This propagates for a while, and then someone realizes, no, that's not enough. You have to decapitate them, right? And so that's the thing that spreads around. And in the end, you get lots and lots of different variants that seem to be exploiting susceptibilities in the underlying network. And we can actually verify this for this particular meme because it starts out as a political message. So what we do is we look at the political leanings of the individuals who are sharing them, -1 being liberal, +1 being conservative, and we just average for all the people who filled that out in their profile and who also shared the meme. And as you might expect, the original healthcare variant is rather left-leaning. Interestingly, the Star Wars and the zombie variants are somewhat left-leaning. Cancer, no one should die of cancer. Everyone gets behind that. There's no political bias for those who spread that. Beer leans slightly conservative. No one should die because government is meddling with healthcare. That's way conservative. No one should have to pay taxes for people who are too lazy to get a job and so don't have health insurance, also conservative. Right? So we see the meme exploiting susceptibilities through these mutations that occur. One way in which we can coarsely get at how large the mutations are is with the edit distance. So for example, if we take this meme and someone is looking at it at 11:30 at night, and they're reading the last sentence, and it says, post this as your status for the rest of the day, and that doesn't seem like it's going to be too effective. So they change it, and they say, post it for the next 24 hours. Same meaning, but it's going to be more effective. And here you delete 14 characters, add 11, something like that. And it's a relatively small edit distance of just 25 characters. Now, if the meme is kind of propagating from person to person to person, and it has this, with each copy, there's some probability that it's going to be mutated, then you expect that the further apart in this cascade the different variants are, the greater the edit distance is as well. And this is, in fact, what we find. So here's just the average. You can see the edit distance increasing. So this is just like the telephone game, where someone originally had a message, they whisper it in someone's ear, and that person whispers it in someone else's ear, et cetera. By the time it gets through to the other end, it's something quite different. Here, it's supposed to be easier for individuals, right? Because all they're doing is really selecting text and copying and pasting it. But the thing is that they often can't resist making little tweaks. So in the end, what we think the mechanism is something like this, right? You have the original, and it's replicating, but then it mutates, and the mutations end up replicating as well. Now, this fits very well a model of biological evolution that was first proposed by Yule in 1924. He was looking at data collected by Dr. Willis in different families, for example, the family of longhorn beetles. And when he looked at the distribution of species per genus, it was this heavy-tailed power law distribution. And this was repeated for different families. For example, for legumes, it's the same way. And the mechanism was very similar to what we see with memes, which is that you have one species. Through mutation, it leads to other species. Every once in a while, the mutation's so great, you get a new genus, and then you get new species within that genus, and so on. Now, he derived analytically that what you would expect for low mutation rates is a power law with exponent roughly 2. And you can simulate the process and see what happens as the mutation rate increases. Basically, the power law exponent increases and it starts to look less and less power law. So the greater the mutation rate, the more equal the distribution of variance. Sorry. So this is what we see empirically with the memes. So each one of these distributions is a single meme, and we're looking at the popularity of the variance within the meme. If we fit the power law exponent to these distributions, so these are memes that have over 10,000 different variants, we get power law exponents close to 2, and for the ones that deviate from this, so some of them don't, a very small percentage don't fit. And if you look at them, it makes a lot of sense. So for example, one that didn't fit was one that said, in honor of Mother's Day, post the names and birth weights of your children. If you think about it, this is going to have an extremely high mutation rate because every copy made is pretty much going to be unique. And indeed, right, that one does not fit a power law distribution. In general, though, we have memes that are smaller where fitting power laws is tricky. So what we're going to do to get the inequality of the distribution is we're going to use the Gini coefficient. The Gini coefficient is typically used, for example, for income distribution. So you line people up from poorest to richest, and you see what is the cumulative wealth that everyone up to this point, for example, has, and that's the Lorentz curve. The Gini coefficient is this area between the line of equality and the Lorentz curve. So for us, if all variants are equally popular, you get a Gini coefficient of 0. This could happen if the mutation rate is 1, right? So each new variant gets only one copy, and immediately, as soon as it's copied, it mutates further. If only one variant is present, there's no mutation. So one variant gets all of the copies, and all the other variants don't even exist. The Gini coefficient is 1. If you have a certain mutation rate, but all the mutations are sterile, that is, they won't produce offspring themselves. This is an extreme form of differential fitness. Only one variant is fit, the other ones can be created, but they have 0 fitness. Your Gini coefficient is 1 minus mu. And then finally, for the Yule process, for low mutation rates, you get this approximation of 1 minus mu over 1 plus mu. Now, we want to measure the mutation rate. So what we do is we look at each copy that was made, and then we look at whether a friend of yours had posted that same exact variant previously. And if they had, then it's not a mutation. If none of your friends had the copy that you have, then we infer that you mutated it. So it is a mutation. And from this, we get a mutation rate and also phylogenetic tree of the variants. And in this plot, this is the plot, we have each one of these points is a meme. And here we have the mutation rate, and we have the Gini coefficient. The blue curve, which is actually valid just here, is the analytical prediction from the Yule model. This is a simulation of the Yule model that's valid throughout the range. The purple dashed line is the Yule model with different fitness, and the straight line is the extreme differential fitness that's 1 minus mu. And so what you can see is that the vast majority of memes actually fit within this range. They're explained by the Yule model, except there's some outliers. And so you might ask, well, what are these guys? How come you're getting stuff up here? Well, this one, for example, asks you to list your place of birth. And we know that places of birth are Zipf distributed, and so, or population centers are Zipf distributed. So naturally, people, even though they're mutating the meme, they will create the same variant as lots of others have done before them. So the Gini coefficient is high, even though the mutation rate is high. So similarly, this is zodiac sign. This is grab the book closest to you and copy this particular sentence out of it. Again, lots of people are sitting next to the same book. And here is our birth weight and name meme. It's exactly where you would expect it, right? You have a very high mutation rate, close to 1, and you have a Gini coefficient close to 0. They might say, well, maybe this is happening, through some coincidence. Maybe it's not this process of a meme spreading and mutating over the network. Well, we can look at a subset of memes where a large fraction of the instances we see are not occurring. We can't find a friend who posted it ahead of you, which means that very likely it's somehow externally driven. So if we try to match the mutation rate we observe there with the Gini coefficient, those are the red lines, we basically see noise. How am I for time? A few minutes? OK. So other cute parallels with biological evolution are that the edits tend to occur preferentially at the beginning and at the end through this copy and paste mechanism. This is to some extent true with genes as well, where the end non-coding regions have higher entropy than kind of the core coding regions. And similarly, the guts of the meme are less likely to be modified than little intro text, such as, hey, this will be fun, or et cetera. We see a little bit of selection pressure for shorter variants of the meme, and this is consistent with the memes not having to have everything incorporated in order to be fit, because there's such a thing as lateral gene transfer. So the phrasing, 97% of you won't, but a few percent will. That actually gets transferred from meme to meme, so not every meme has to carry that. So you end up having shorter variants being slightly preferred. One last mystery is, why do different variants peak at different times? So here we have what I call the bladder meme, or the appreciation meme, where someone in some sort of public service is helping your family, but they have to hold their bladder. And sometimes it's a nurse, and sometimes it's a cop, and sometimes it's a firefighter, right? But if you look at the popularity over time, over a year, right? Sometimes it's the nurses, sometimes it's the firefighters, then all of a sudden, whoa, it's the cop variant that's most popular. And how could you even have predicted this? If you look at the no one should meme, similarly, different variants peak at different times. There's even one time when the Star Wars variant becomes more popular than the healthcare variant. And we simulated the Yule process over a network. We chose a relatively small country with about 2 million active Facebook users, and we just simulated what would happen if you had this kind of process. Now, if you have people kind of with different activity levels, but the whole network is complete at the start of the period, what you get is that different variants do peak at different times, but it's all over relatively quickly. It doesn't go on for years and years. However, if you allow nodes to join over time, in fact, kind of providing fresh susceptibles, then you get a broader peak, but not really different variants overtaking at different times. And finally, if you allow different variants to have different fitnesses, then you get something like what we observe in the empirical data, which is that you can have later occurring variants and mutations experiencing peaks later on in the cycle. One final mysterious thing, but that again has links back to biology, is recombination. So there's an anti-bullying meme that's been copied 300,000 times, and there's a sick child meme that's been copied 100,000 times. Someone pastes them together. It's not clear why, but this actually occurs rather often. And the combination, as is copied 10,000 times, right? And just like these kinds of string operations keep occurring in a way that you imagine they do in biological evolution. So to recap, I told you how social networks filter information via this nice experiment, but also how this process causes the information to evolve. And so the only possible conclusion is that, it's alive or sort of alive, this information that we ecosystem that we coexist with. Finally, what I wanted to say is, if your Nature paper gets a little bit misunderstood by Nature, there's this wonderful new journal, Network Science, so please submit to Network Science. Thank you.